Okay, this is Psych 222. It is Friday, January 15th, and this is our second complete lecture. Just a couple class notes before we get started for today. A reminder that for the Zoom labs on Thursdays, that link is available right on the syllabus. So if you go down to where the lab section is on the syllabus, you will find the Zoom link. And all you have to do is take that link and put it into your browser, and you will be connected to the labs. Okay, so that's all in the syllabus. The other reminder is that assignment number 1 will be posted today. So in line with what the schedule is for the course, you're going to be working on assignment number 1 until you go to lab next Thursday. So next Thursday, Gabrielle is going to look at assignment number 1 and talk about potential solutions to the assignment, discussion, and all of that. So that assignment is going to be posted today. So you're going to get that. The other reminder is that we are going to be starting into the textbook on January 25. So you should all have your textbooks, and if you don't, make sure you have them because that date is fastly approaching and we're going to be right into the book pretty soon. Okay, before we get started on today's stuff, because we want to review some matrices today, some of the precursors to studying statistics is a little bit of background in mathematics. Much of which you've probably seen before, but we want to discuss it a little bit. But before we do that, I thought it'd be interesting to provide a little bit of motivation for that, because once we start talking about matrices and calculus, those topics can seem a little bit dry at first, and you might want to know why we need to study any of this stuff, including statistics, right? Why do we need to study any of this? Well, perhaps there's no better motivation than the actual COVID-19 pandemic, okay? And if you want to understand research articles in psychology, in business, in chemistry, in biology, you really need to understand the statistics. There's really no way of getting around it. You have to understand the stats. So here's an example of some statistics used in a research article that is extremely relevant for today, which is the effectiveness of the COVID-19 vaccine. And you've undoubtedly heard about this. This is the vaccine presented by Pfizer, and this was confirmed for use on the population in December. And this is the original article that Pfizer published in the New England Journal of Medicine for the effectiveness of that vaccine. So you've heard about it on the media that it has like a 95% effectiveness rate. And maybe you've heard some other things about the vaccine. If you want to understand how they got those figures, you're going to need to understand the stats. So we're not going to go through all of this article. Much of it, you need more statistics to understand. But if you look through this paper, you'll see that statistics are everywhere, okay? So we see over here, the results of the study that they did an experiment in this case. Now the experimental design is, if I put that E over here, they're gonna have a control group and a treatment group. So the control group in this case, we're gonna look at the results in a second, but the control group in this case just received some kind of a placebo. And the treatment group, well, they received the vaccine. And then what they did in this study is they observed how many people actually got the COVID-19 virus, right? So what would you expect to see? I mean, what would be the ultimate result here? What would be the best case scenario? Well, the best case scenario is that everybody who got the vaccine, right, the treatment is the vaccine. What would be great is if nobody's getting the COVID-19 virus, right? And those in the control group who did not receive the vaccine, whatever numbers they're using, and we'll look at their numbers, but let's say it's 100, right? So say 0 over 100 and 100 over 100, that would indicate perfect effectiveness of the vaccine, right? Because 0 people are getting it in the treatment group. Now, and 100 people are getting it in the control group. So that would suggest that the vaccine is working. Now, a couple of things to notice about this is the first thing to emphasize is that it is an experimental design, which is really, really important. Why do you need an experimental design? Why do you need to randomize subjects? So there's a subject. And the process of randomization, we're going to talk about that in the book, and you'll see it in the book, and you can underline it in the book, and we'll look at those definitions. But conceptually here, the process of randomization is taking people who are participating in the study and just randomly assigning them to group. This person goes to the control group. Another person goes to the experimental group over here. So you're starting off with a pool of subjects and you're doing an experiment, which means you're randomly assigning to groups. And then you're observing the result. This type of design here is really, really important because if you do not do an experimental design for something like the vaccine success rate, then you're not really going to know whether the vaccine is working, right? So imagine if you decide to not do an experiment and you just started giving the vaccine to people and kind of just observe whether they get COVID or not. Then you don't really know what's going on in a control group. You don't know what's going on in a comparison group, right? So let's say that you just did this and that you had no control group. So for a moment, we're going to pretend like you just gave the vaccine to 100 people and you had no control group. Let's say that 0 out of 100, which again is a really good result, right? 0 out of 100 are getting the virus. Even if that happened, you would not necessarily be able to say that the vaccine is working. Why? Because you don't have the comparison group. It's entirely possible that in this particular setup, maybe this would have been true for the control group as well, right? You see the importance that if this is 0 out of 100, maybe if they didn't even receive the vaccine, it would still be 0 out of 100. You don't know unless you have that control group. Now, we could probably conclude that it probably wouldn't be 0 out of 100, right? Because we know that people have been getting COVID-19, getting the virus. So that would be kind of taking it to extreme a little bit here. But you understand the principle is that if you don't have the control group, you cannot compare that effectiveness of the treatment. You absolutely need that control group. Maybe as a more realistic example, what if this were 20 out of 100? Again, 20 people out of 100 getting the COVID-19 virus. We don't know if this is being effective for the vaccine because we cannot compare it to a control group. So in the control group, maybe just by receiving nothing, people are also getting the COVID-19 virus, and that number is equal to 20. In both cases, you need the control group, so you need to do this comparison. And we will talk more about this idea of an experimental design as we go, but that's really, really vital, because otherwise we just don't know. So if you look at the results here, let's just look at what they did. They took a total of about 43,500 participants, underwent randomization. And you see what the randomization is here, is they're taking the people and going to the control or treatment group. There's no bias involved here. So they didn't take this person and say, you know what, you look like you would go well in the control group, right? That would be completely biasing things. They took this person and they basically flipped a coin or some other random method to ensure that this person going into the control group is going there purely by chance, right? There's just chance operating here. There's no good reason why this person goes into the control and this person goes into the treatment. That has to be randomized. So when you think of randomization here, you're thinking about that element of chance. They're being assigned by chance by a random process. And that is very important because you don't want to take certain people and put them in one group because maybe there's going to be a bias there, right? Maybe, what if this person is 85 years old? You know, we know that COVID-19 is affecting the elderly a lot more than younger people. So if you started putting this person on purpose into the control group or the treatment group, you'd be biasing things. So you got to have that process of randomization. And again, we're going to develop that in the book and all of these principles. We're just kind of getting the feel for these things right now. Okay. 43,448 received injections. 21,000 with, this is the actual name of the COVID-19 vaccine. And this is the number who received a placebo. Now, the placebo is often like a sugar pill or some kind of almost like a dummy pill. And that's just so it kind of both groups are getting something, but what this group is getting here for the control, it's not having any effect. It's just like just taking like an empty pill or something like that. So that's often used in experimentation. Other things in here, they talk about subgroups of people, right? So when we hear that the COVID-19 vaccine works, well, you might want to know, does it work across age? Does it work across sex, or race, ethnicity, etc.? Because those things over here, you know, maybe all these things have an effect on whether you get the virus. And one thing is, we know that age is going to have an effect. We've been hearing about it all the time. So it makes sense to kind of get some subgroups in there. And they do that in the article as well. What were their conclusions from the study? Well, they have a 2-dose. You may have heard that it's a 2-dose for the Pfizer vaccine. I think there's another one coming out where the Johnson & Johnson vaccine, apparently you're only going to need 1 dose. But they say there's a 95% protection against COVID-19 in persons 16 years of age or older. So let's just go to the end of this article and just look at what that 95% protection means. One of the first things to realize is that 95% is not 100%. This is not 100% protection. So we want to kind of look at, well, what's that other 5% doing, right? What's that other 5%? And if you read through this paper, and you can access it on the Pfizer webpage, they detail exactly how the study was done. And you're going to find that, again, to motivate the course a little bit, to understand a lot of this stuff, you're going to need some statistics background. Like we're going to need to understand what these little bars are over here, which are error bars, but we're not quite sure what they are yet until we actually have a course in statistics. So all of this stuff is really, really interesting, and we need to know the stats. We need to understand the stats so we can actually critically evaluate their study and make sure it was done properly, and maybe even make a recommendation to maybe some of your family members of whether, you know, they should take the vaccine, because you know the stats behind it. You studied the actual original research. So imagine if you're able to say that to your family members, say, I've studied the research, I've looked at it, and it looks pretty sound. So there's your motivation for looking at statistics and understanding it. Now they present this table too right here, where they cite the vaccine efficacy against COVID-19, and they present a table here. I'm just going to go to a different slide right now and look at how they computed it. So this is the same table. I just put it on a different slide just so I can write all over things a little bit here, and also explain what's called the attack rate. So how are they getting this 95% efficacy? So the first thing is, when you look up here, don't worry about anything else other than this 95%. This is what we want to understand, because that's what's been cited in the media. And we've heard it many times that it's been 95% effective. So the first thing in this table is we see the vaccine name. That's the name of the treatment. And there's our placebo right here. Okay, don't worry about surveillance time, something a little bit different. What we're interested in is the number of cases. There's the total number of cases. Now, the first thing is we notice the number of cases are not equal to one another. That shouldn't be a problem. And as we're going to see, it's not going to be a problem. Here is the COVID-19 occurrence at least 7 days after the second dose in participants without evidence of infection. So in other words, you're getting COVID-19 here. That's what that's saying. After the second dose. But this means you're getting COVID-19. Well, out of 18,198, okay, how many people got the COVID-19 virus? 8. So 8 people out of 18,198 who received the vaccine, and these people all received the vaccine, are still getting COVID. This is something else. Won't worry about that. We're just interested in these two numbers right here. Well, let's compare that to the control group, right? To the placebo group who got something like a sugar pill. That's the kind of like the dummy pill. 18,325, that's the total number in the placebo group. Number of cases that got the COVID-19 virus is 162. So we got 162 out of this number in the placebo and 8 out of this number in the treatment group. So let's just think about that for a second. Again, get rid of this. Let's just think about that for a second. What's our first impression, right? What's your first impression of this? Well, the first impression is what? Well, let's conclude a few things. First of all, we can see that more people are getting the COVID-19 virus in the placebo group than in the treated group. 162 versus 8. But at the same time, the numbers are slightly different here for the numbers in each group, right? So if you look at the 18,325, well, that's a bigger number than 18,198. It would be nice if those numbers were equal, right? It would be nice if those numbers were equal. Then you'd be able to just compare these two things and have an idea of what's going on. But the thing here is that this number is bigger than this one. So you can see that if this number is bigger, you kind of expect this number to probably be a little bit bigger than this one because there's more people tested here. Right? I hope that makes sense. There's more people tested here than here. Therefore, it seems reasonable that this number should be bigger. Now, that much bigger? Well, this one's 8 and this is 162. So this 162 is not due to just having a bigger number here, right? It's not due to just having a bigger number here. It definitely looks, when we look at this data, when we look at this, we say 162, that's probably because they're getting the placebo. It looks like there's, they're not getting any treatment, so the number is higher. If you're in the treated group, only 8 people are getting it. So our first impression from this is that it looks like that vaccine is having some kind of an effect. Now, what effect it's having, we don't know because we'd have to talk to the biologists, right? What's the mechanism underlying the effect? What's that vaccine actually doing, in your body to reduce the occurrence of COVID-19? None of that is in here. These are just the numbers. But the people who developed the vaccine will be able to, tell us more about that, the mechanism behind it. So the mechanism behind why we're seeing this difference in numbers is really important. This is just telling us that you have different numbers. Okay, so we want to be able to get this 95% efficacy rate because that's what they're telling us is true about the vaccine. So how do we get that? Well, here are some vaccine computations of how we actually get the effectiveness rate of a vaccine. These are called attack rate calculations. And here, this is COVID-19. Okay, so it's for a different virus, but this is COVID-19. So just replace that with COVID-19. And what this says is COVID-19 during the outbreak. Do you get the virus or do you not get the virus? And this is the vaccination status at the start of the outbreak. So these are the people who are getting vaccinated, and these are the people who are not vaccinated. You can see that that aligns up with these two groups. This is exactly what we're seeing up here. Vaccinated versus placebo. Vaccinated, unvaccinated. These people are unvaccinated. These people are vaccinated. And then you can see what the numbers represent. How many people are getting the actual COVID-19 virus in the vaccinated group? Well, what is that number? 8, right? 8. What's the total number? 18,198. Okay? And then that's just the balance of that. And you see over here, we have in the placebo group, how many people are getting it? Right there, right? 162 out of 18,325 right here. Okay. So these are called attack rates in the vaccination lingo. So we have the attack rate for the vaccinated, attack rate for vaccinated. That's A over A plus C. There's our A plus C. That makes sense, right? We're taking this number over that total. Notice it's important to put that total, right? This is the point we made earlier. I can't just compare 8 to 162 because I have to know what are those totals based on. And this is what this table is telling us. A over A plus C. B over B plus D. So the attack rate for the vaccinated, okay, the attack rate for the vaccinated is A over A plus C, right over here. And the attack rate for the unvaccinated is B over B plus D. So we have both rates over here. And why do they call it the attack rate? Well, kind of makes sense that they would call it that, right? The attack rate, because that's, are you getting the virus? How much is that virus attacking you in terms of whether you're vaccinated and unvaccinated? If you get the virus, it means you've been attacked. That's why they're calling it the attack rate. So based on this, we have a couple of rates, and we want to look at the effectiveness of the vaccine. So how are we going to get that effectiveness of the vaccine? Well, let's look carefully at their formulation for this. First of all, we notice it's a percentage that they're going to have because that's what they cite. They cite it as a percentage, a 95%. But let's see what the computation looks like, and then we'll kind of discuss whether this computation makes sense, right? It should make sense to us. Whenever you look at a formula, it should make sense. If it doesn't make sense, then we got to understand the formula in a little bit more detail. Here's the wrong way to study stats, is to just memorize formulas. That would be the wrong way, because if you just memorize the formula without understanding what the components of the formula are, you're never going to be able to generalize your knowledge, and you're not going to really learn the concepts. Okay, remember, you got to understand the concepts. Don't just memorize a whole bunch of stuff, and don't just memorize the formulas. You got to understand the concepts. And if you start doing that, then you can look at almost any formulas and kind of break them down to see what they're actually accomplishing. So this says the attack rate for the unvaccinated minus the attack rate for the vaccinated divided by the attack rate for the unvaccinated. The times 100 is just to get it into a percentage. So that's not of primary importance here, right? That's just getting it into a percentage. Otherwise, it'll be left into a proportion. So this isn't exciting. That's not what the formula, I mean, that's, we're not looking at this formula saying, wow, times 100, that's not very interesting. What's interesting is what's going on here. Here's a way of looking at this formula. Let's say that the attack rate for the vaccinated, right? Let's say that the attack rate for the vaccinated is 0. Wouldn't that be the ideal? That would be the best case scenario, right? I mean, if the attack rate for the vaccinated were equal to 0, that would mean of those who are vaccinated, how many people are getting the virus? 0. 0 over the total. Best case scenario, most optimal result. Well, if that's what happened, this would be 0. And then whatever your attack rate for the unvaccinated is, would be divided by the attack rate for the unvaccinated, because these two things are the same. So you'd have attack rate for the unvaccinated minus 0 over attack rate for the unvaccinated. And what would that equal? That equal 1.0, right? You get the same number because this number would equal this number. Multiply it by 100 just to get the percentage. But again, that's not the most interesting part. Most interesting part is what's going on here. Now, doesn't work out that way. You're going to get the attack rate for the vaccinated is going to be higher than 0. It's not going to be equal to 0. It's going to be higher than 0. As we saw in our computation, it's higher than 0. So it's not perfect. So you can see what that formula is doing. But the point of this discussion briefly is to say that if you allow certain numbers to go to their extremes, you can tell what the formula is doing. The most optimal result would this be 0, and therefore you're going to get 100% effectiveness. What are some other things we see in this formula? One thing is we hope that the attack rate for the vaccinated is less than the attack rate for the unvaccinated. Let's hope on that, right? Because that would be a pretty bad vaccine if the attack rate were actually higher for the vaccinated than the unvaccinated, right? Imagine that. Imagine if they gave you the vaccine and more people who received the vaccine got COVID, right? What would that represent in the table here? That'd represent, like, imagine if this was 162 and this was 500, right? Imagine if this was 500. Not only is the vaccine not working, the vaccine is maybe helping you get COVID-19. So that would be an absolute disaster. So that's why in our formula here, we're expecting that attack rate for the vaccinated to be less than the unvaccinated. Right? Now, again, the ideal is that it would be 0. That's hardly ever going to happen. But we wouldn't want this to be actually bigger. So this number won't be 0. It'll be a number greater than 0. But we're hoping that this is kind of bringing it down from here, from the unvaccinated. So you can see how we're getting that vaccine effectiveness. If you look at the data, the numbers for our current example for what they actually did. And again, this is the real study that they did. This is what you've been hearing about in the media in December. As soon as they announced the virus, or November, whenever it was, this is the actual report on which we are being given that vaccine. This is it. The justification for why we're getting that vaccine is this data we're looking at right now. That's how important it is to understand the stats. So the attack rate for the vaccinated, well, I computed it, 8 over 18,198. Attack rate for the vaccinated is, that's what I got right here, 8 over 18,198. There it is. Again, you can look at it this way too. A over A plus C, 8 over 18,198. There it is. Attack rate for the unvaccinated, 162 over 18,325. That's 162 over 18,325. So what I've done here, I've done the computations for the attack rate for the vaccinated, attack rate for the unvaccinated. Now, how do we get the vaccine effectiveness? VE, that's the vaccine. Oops, That's the vaccine. I'm running out of space. Effectiveness right here. How do we get that number? Well, I just did the attack rate for the unvaccinated. I followed this formula. 162 over 18,325. That's for the unvaccinated. Minus attack rate for the vaccinated. Right? There's the attack rate for the vaccinated, 8 over 18,198. I took all that and I divided it by the attack rate for the unvaccinated. So we got to be careful. We get our brackets here. We're doing this first up here. There's our numerator, and there's our denominator right over here. And when you do that, you get 0.95 times 100. That's the times 100 right there. That's why, you remember I said that times 100 isn't that interesting. Well, you got to put it in to get the percentage, otherwise it's going to stay as a proportion. Again, when you look at a formula, the tricky part is to focus on the most important parts of the formula. What is the important part? The times 100 just gets it into a percentage. That's not the exciting part. The exciting part is the attack rate differences over here. And that's how they're getting the 95%. So when they say the vaccine has a 95% effectiveness rate, this is how they're computing it. A couple things to note about this. If you're a researcher and as a scientist, or just a consumer of the research, you're looking at this and, you know, what are some follow-up questions? Some follow-up questions are, you know what, there's 8 people, right? There's 8 people who received the vaccine who still got COVID-19. That's interesting, right? As a researcher, that's very interesting because that vaccine is apparently not working for everybody. So what you might want to know as a further investigation is, what is it about those 18 people or those 8 people, right? What is it about those 8 people that makes them different than the people who didn't get the virus, right? What is it about those 8 people that's maybe different than people who didn't get the virus receiving the vaccine? That's a really, really interesting research question. And I guarantee you, those Pfizer people, they're on it. We don't even have to ask them. They are on it. They are wondering, why did they still get it? And there will be so many papers published on that to find out what differentiates the people who get the virus versus not get the virus, who still got the vaccine. Other things over here, the placebo, other follow-up research questions, is 162 got the virus, but there's a whole bunch of people who didn't get the virus, right? Interesting. 162 got a whole bunch of people who didn't get it. Why? What's the difference between those people? Is it the fact that maybe these people, well, I mean, we could list the possibilities. These people here, maybe they've spent more time in social settings than the others. Hopefully they screen for that a little bit, or maybe they have weaker immune systems, or maybe, what's another one? They have other factors, other health conditions, right? Or maybe they have a different genetic makeup, or a whole bunch of things that they would want to look at on a research level as to what's going on with that. Okay, so that's an example of where statistics are needed, where understanding formulas are needed, and really no better example than what's going on with COVID-19. And this is probably, you know, this COVID-19 paper is probably one of the most important papers published in the last many years because of this COVID-19 pandemic. And if you understand statistics, if you understand what's going on in experimentation and things, you can interpret papers like this and evaluate them for yourself to try to find out, you know, whether they did a good study, whether it's a standardized study, whether it's very scientific. One more thing to note before we leave this is look at these numbers, okay? Now that's 18,000 about, and that's 18,000. What do we notice? That is not that big, right? So we're testing out this vaccine, or Pfizer is. Pfizer is testing out this vaccine on what? Let's draw it. A sample. right? They're testing it out on a sample of observations. But are they interested in the sample? Not really. They're interested in what? The population, right? The population. It's going to be chapter 1 in the book coming up. Sample, population. These are the elements of the sample right over here. That's all the sample. But what they really want to know is what is it going to do in the population? Now, does that sound familiar? Well, it might sound familiar because that's exactly what we talked about in our previous lecture. What are they going to have to do? They're going to have to make an inference. Induction, right? There's going to be inductive reasoning. Inductive reasoning being taking place here. There's going to be an inference. What's the nature of the inference? I'm going to use the analogy, and you're going to see how it connects with what we talked about last time. The aliens see 200 dogs with 4 legs. Therefore, let's take a good guess that all dogs have 4 legs. Does everyone see the analogy? Okay, let's go back to COVID-19. Here's the success rate on the vaccine. It's 95%. That's based on the sample. Therefore, if this is the success rate based on the sample, let's make a pretty good guess that it's going to apply in the population. Inductive inference. Okay, it's an inductive inference. Okay, so what happened with the dogs? What happened with the dogs? Well, the aliens saw those 200 dogs, or whatever, pick a number, 200 dogs, and what did they notice when they went out into the population? Yep. What did they notice? A 3-legged dog, right? They noticed a 3-legged dog, even though in their sample, they had 200 that had 4 legs. They noticed a 3-legged dog. That's the problem of science. Now, what's the 3-legged dog in the COVID-19 vaccine research? This person here, the vaccine maybe had a side effect or something like that. You know, there may be a case for which there's a complication, right? That complication is kind of like the 3-legged dog. So the point is that when you take the sample information and you infer to the population, that's not going to be a perfect process. There's going to be some error involved. Why is there going to be some error involved? There's going to be some error because you only have a limited number of observations. Even though 18,000 is a nice sample, that's a pretty big sample, that is not nearly representative of the world population. It's not representative of American population. So they don't quite know what it's going to do on the population, even if they have a good idea of what it's doing in the sample. Now, that doesn't mean we shouldn't take the vaccine. That just means that there's going to be some cases here and there for which might be a little bit surprising, or they're going to learn more about the vaccine just by giving it to the population. And that's the nature of inference. We can't get away from it. Scientific inference is like that. When you go from the particulars to the more general, it's usually not going to be a perfect match. It's not going to be a perfect match. Now, the Pfizer researchers, they can most likely quite confidently say that it's a very safe vaccine because they made sure that the sample had a pretty wide array of people in it with different backgrounds and things like that. So it's probably going to do just fine in the population, but you're still going to get some people who are allergic to it and other things like that. Okay, so there's an example of why we need to learn stuff like this. There's the motivation for looking at some of the matrices, because some of this could be a little bit dry, but if you understand where it's going, you understand why these tools are necessary. and why if you go into psychology or any other areas of science, you really need to understand the stats well. So let's start our brief review of some mathematical concepts. And again, some of this can seem a little bit dry at first, but we'll see how they're used eventually in the stats book and things like that. Some of this may look familiar as well. So we're going to start off with some of these matrix ideas. Matrices, linear algebra, and vector geometry. We're not going to talk too much about vector geometry, really. So you can take that out, and you can take all of this out over here. We're just going to focus on some of these elements. The real stuff that I want to get to in these notes are the calculus concepts over here, and which we're going to start into next week. But it's still good to look at the matrices a little bit. There's other elements of the appendix that we're definitely not going to go through. We're just going to touch on a few parts over here. And again, you know, you don't have to memorize this stuff. Just follow along with it, discuss it in lab a little bit. We'll give a couple assignment questions, but you definitely don't, this isn't stuff to be memorized. Just kind of understand a little bit what we're talking about, and some of it will look familiar from previous classes as well. So what's a matrix? We talk about matrices, we talk about a rectangular table of numbers or numerical values, right? So there's a matrix right there. That matrix has 4 rows and 3 columns. So 4 rows and 3 columns. Now, what are these numbers? Well, these numbers could be anything. Maybe we have IQ data. So maybe this is like a verbal score, this is a quantitative score, and this is your score on an analytical test. Now, these numbers don't really represent things like that, but you can see that we use matrices like this so we can contain a lot of numbers in the object, right? If I only have one piece of one variable, like just verbal scores, well, then I can just have, you know, one little matrix like this, which we could even call that in a second, we'll call it a vector. But if I have a lot of data, well, I need a matrix. So even when we work with data files and stuff like that in data analysis, we're actually working with these big matrices. So there's an example of a matrix, and it's got the rows and the columns. More generally, we can state the matrix in symbolic notation, so we don't actually have to put the numbers in it. And what these subscripts mean here is row 1, column 1. That's row 1, column 1, row 1, column 2. And what are the A's? Well, those are elements of the matrix A. Okay, so elements of the matrix A, and we use MN to denote for how many rows and columns we have. Okay, that's why you'll see in matrices, you'll see that notation there, because we're not quite sure how many we're going to have. So this is a very general notation. Talked about vectors. Okay, so there's a column vector right here where we just have a single column, and this is called a row vector. Okay, a row vector. Now, I'm going to talk about what this is right now. This is called the transpose. So if you take a column vector and you put it as a row vector, well, what you're doing is you're doing the transpose of a matrix. And the transpose is denoted by A prime. Okay, so if we have our X matrix that we just looked at, well, instead of just X, we're going to move it over, make the columns the rows and the rows the columns. So we're going to have a 3 by 4 over here, and there it is in general notation. So that transpose is denoted by the prime. Sometimes you'll see this too, AT for transpose, depends on the book. One thing to keep in mind when you're looking at mathematical and statistical notation, remember it's not constant from book to book, author to author. You can't just look at the symbol here and say, well, whenever I see this symbol, it means transpose, right? Whenever I see this symbol, it means transpose. This can mean a whole bunch of things depending on the context you're looking at. Square matrix of order n. So a square matrix has n rows and n columns. It's got n rows and n columns. So there's an example of a square matrix. It's 3 by 3. What's the trace of a matrix? Well, the trace of the matrix is the sum along this main diagonal of the matrix. And it may seem kind of weird right now that we want to calculate something called the trace, but if you go on into statistics, you'll see that the trace is actually very, very necessary and useful in some contexts. So if I talk about the trace, then I don't have to tell you what I'm doing. I can say the trace of the matrix, and then you'll say, well, you're summing these values. And look, if this matrix is 3 by 3, imagine if this matrix was 100 by 100. In data science and machine learning and things like that, they do with like matrices of 1,000 times 1,000. Your computer on which you're viewing this video is computing matrices all the time. And they're computing of a really, really big dimension. So computer scientists will study matrices and things in very, very big dimensions. So if you have to compute something called the trace, you could be summing across 1,000 different values and more. Square matrix is symmetric if A is equal to its transpose. So the elements ij is equal to ji. And again, those are those subscripts. So negative 5, 1, 3, 5, 1, 3. Notice that the row is the same as the column. The row is the same as the column, and so on. That's what it means for a matrix to be symmetric. We have upper triangular matrices, lower triangular matrices, upper triangular matrices. It's got numbers up here, and it's got zeros over here. Zeros below its main diagonal. Lower triangular matrix, same idea, except it's lower instead of upper. Diagonal, all of these values are 0, and then you have numbers along here. Okay. A few other terms here. A scalar matrix is a diagonal matrix of whose diagonal entries are equal over here. So this particular matrix here is an example of a scalar matrix, but it's called an identity matrix because there's ones along the main diagonal and there's zeros everywhere else. That's called an identity matrix. And the identity matrix roughly corresponds to the number 1 in ordinary algebra. So remember when we talk about the number 1 in scalar algebra, we talk about ordinary algebra, we often say it's scalar algebra, and that identity matrix has a correspondence to the number 1. So you see that the matrix is a generalization of these concepts that you see in ordinary algebra. Okay, some other things, you have the 0 matrices where you have all numbers are equal to 0 in the 0 matrix. So maybe you have something like this. They're all going to be zeros, and just like the identity matrix is kind of equal to 1, well, the 0 matrix represents 0 in ordinary algebra. Okay, so you see a lot of these things generalized. We're not going to talk about partition matrices, so we put an X here to say we're not going to talk about that, but you could read on that if you wanted to. It's not that important. We can do simple matrix arithmetic, so we can add matrices, and we can subtract matrices and do a whole bunch of operations on them. So, if we were doing just regular arithmetic and algebra, well, there's arithmetic, that's equal to 1. But if I'm doing algebra, I can go A minus B, right? I can take whatever A represents, whatever B represents, and that's equal to something. Well, I can do the same thing in matrices. So there's my matrix A, there's my matrix B. I can identify a new matrix called C and say that that's A plus B. I can identify another matrix, D, and say A minus B. And how am I getting these computations? Well, A plus B, A plus B, A plus negative 5. Well, what's 1 plus negative 5, right? 1 plus negative 5, well, that's 1 minus 5. Remember, when we're saying things like this, we're still adding it, but we usually just say 1 minus 5. So that's how we're getting the negative 4. Same thing here, 2 plus 1 is 3, and so on and so on. So we're doing this element by element in the matrix to get these numbers. And we could also identify another matrix, this one called E, is the negative of B. So what's this is negative of a -5 is equal to 5, -1, and so on. Incidentally, these letter names here, C, D, and E, those are just used for convenience. There's nothing special about C and D and E here. They're just used for convenience. Okay, couple other things here we just want to look at before we finish up for today. A plus B is equal to B plus A. So that's called the condition of addition is commutative. So if I take a number here, let me just put it in ordinary numbers for a second. 5 plus 2 is equal to 2 plus 5. That's what we would do in ordinary scalar algebra. In ordinary algebra, we'd say the conditions like that. Well, the condition is the same thing in matrices, which isn't surprising, right? That kind of makes sense that that should hold. This condition is called associative. So you see what the associative means. A plus B plus C, do the stuff inside the brackets first. Do this inside the brackets, but where you put the brackets here isn't going to matter for the addition. That's what that means. So it's a property of matrices that these two results are going to be the same. Other properties, A minus B is equal to A plus minus B. That's what we just set up above, right? And that's also equal to this. Some obvious properties, right? A minus A is equal to 0, A plus 0 is equal to A, and so on and so on and so on. Okay? So there's a few other rules here. We'll continue talking about these things next time, including the distributive property over here, because we know the distributive property works in A, B plus C. We know we can distribute AB plus AC. Well, that's the same thing in this idea of using matrices. So again, many of these things simply generalize from basic algebra. We're just applying them to bigger things in matrices. Okay. So for next time, you can read ahead a little bit, and we will just cover this really quickly next time to finish up our brief matrix algebra review. But we want to definitely look at the inner product. So this is something to read over. We want to look at conformability for multiplication. We'll talk about that briefly next time. And you don't have to know this. You don't have to know the powers of the matrix. Okay, so that is definitely not of interest. And we'll talk about the sense behind matrix multiplication next time. We'll talk about inverses. That's something we want to touch on briefly. And you can skip that part. That'll be almost as much as we're going to cover for the linear algebra review. And then we're going to get into the calculus review. So that gives you an idea of some stuff to kind of read for next time. And if you have more time, you can start reading that calculus section, because we're going to get into this calculus section next week, because that's really, really important for understanding statistics. Okay, so that's it for today, and we will see you next time.